rocket, if you push a gas one direction,
I'm not very...
namely downwards out of the rocket.
Nobody always...
Ça fait deux géants dans le pays. Les deux battants de la porte se sont fermés devant Ronaldo. 21e minute. Toujours 0-0 entre la France et le Brésil.
The free kick has been awarded in favor of Brazil. And Robert Carlos is going to take that free kick.
Et un coup franc donc.
You see how this free kick...
En faveur du Brésil. Car je note parce que à cette distance-là, ça ne fait vraiment pas peur à Roberto Carlos. Et d'ailleurs, déjà au ballon qui va le poser, regardez, il pose avec application. Il n'y a plus de balle dans le ballon, hein, parce que mais il a choisi l'endroit où le gauche presque pas ce ballon. C'est-à-dire qu'il va frapper presque extérieur du pied. Et attention à la trajectoire, Fabien. Extérieur du pied. Et il s'est pratiquement en face de et un but sensationnel. La façon dont il s'est placé devant le ballon, les Saouliens qui avaient frappé de l'extérieur du pied. Et il a mis un but, une frappe somptueuse extérieur du pied qui contourne le ballon. Regardez, on voit qu'il va sortir. Et avec les pieds, tout
You can see how it has gone. And in fact, it has really started on a post and then gone out.
donné à ce ballon par la
So
frappe
this
de
is
Roberto
what
Carlos.
is known as Magnus effect.
Candela.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin. Whoa, look at it go!
One day to get back in the water, dude.
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we have no idea that was going to do that.
And this is where I come in. The basketball was subject to the Magnus effect, which affects all rotating balls or cylinders as they fly through the air. And it works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball's spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way. And this is known as the Magnus effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, you know, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat, but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once, and then it crashed.
Okay, I shall talk about one more thing before I finish. 5 minutes. 5 minutes. I shall talk. Can I have the lights, please? Just I'd like to quickly show you. What happens, you know, when we people walk, we really have our arms swing like this, okay? And you will find if our hands are tied up like this, it's very uncomfortable to walk. That is basically because of the fact when we are taking a step like this, basically I am standing on it, for a short time I am standing on one leg, and in the process my arm comes like this to keep a balance, so that I more or less manage to keep my CD passing, whole weight passing through this leg. Now what happens, interestingly, if we can really, our arms are like physical pendulums. It's physical pendulum hinged at one point, so they can really swing like this, and if we really make a quick calculation, you will find, that's what I really wanted to show you. Sorry, let me. This is a physical pendulum. You can find that center of its time period can be calculated easily. But I'd like to show you quickly what we are doing. If we really consider, normally we know from physiology, the weight, mass of the arm is about 5% of our body weight. For women it is slightly lesser, for men it is slightly more. From that calculation, roughly if one person is, as you can understand, is 70 kg, his arm mass is about 3.5 kg. So if you really find out the time period of oscillation of this physical pendulum, you'll be able to find out how fast we are swinging, and during a complete swing we take 2 steps. And if we are taking about, say, roughly 70 centimeters, 75 centimeters in one step, so time period comes out to be about 1.3, 1.4 seconds. So we are taking 2 steps in, in 1.3 seconds. That way we can calculate our speed of walking. Now you will appreciate a very interesting thing. I'd like to show you a small video clip. That will be the last one. That we can really estimate our speed of walking only from this. That means the idea is that you measure my time period of swinging of my arm. You just measure this. You measure the steps I am taking, and I am taking 2 steps in one complete time period, that is in 1.3 seconds, and you calculate my walking speed of walking. That will come out to be absolutely normal. Now what happens when I am running? I am running at a faster rate. I am taking the steps much quickly. You will appreciate that if you look at the 100-meter sprint where Usain Bolt has won, you will understand why his arms are swinging so fast. When his arms swing so fast, his time period becomes lesser. He takes 2 steps in a much smaller time, and in the process achieves a much higher speed. That's what I would like to show you. The way his arms are swinging.
In 2009, the Chambers, Burns, Bailey, Bont, Powell, Patton and Thompson.
Faster rate, which indicates they are taking 2 steps at a much quicker succession. In the process, that increases their speed. So, if someone really wants to increase his speed, he will have to swing his arms in that way only. When we are walking, our arms can swing in a particular way. When we are running, those must swing at a much faster rate, much quickly, with a shorter time period. There are more things, of course. I must stop here. I know the time is up, so I am indeed thankful to you for your patient hearing. Thank you very much. Thank you.
I'm sure you will all agree that this was an absolutely fascinating lecture, and especially for the children, I can assure you that this is something which is giving you an impetus that for doing good in sports, we should understand some physics. Maybe next year when you will all come here to this National Science Day, you will be able to improve on your score, whether it is in cricket, whether it is in football, whether it is in pole vault, or whether it is in long jump and high jump. It's unbelievable how physics plays a role in all these sporting activities. Let's all join in giving a big hand to Dr. Bhupati Chakraborty for this fascinating talk. Okay, I think we cannot afford to wait anymore because we have got a rather packed program. So we are going to start the excitements in mathematics, queen and servant of science. Dr. Ghosh. Let's welcome Dr. Ghosh.
Honorable Director, Professor Bhattacharya, esteemed faculty members of this reputed institution, dear students, ladies and gentlemen. It is indeed a proud privilege for me for getting this opportunity to deliver a lecture on National Science Day event at an institution with which I was very intimately connected. And I thank the entire organizing team, including the chairperson, Professor G.P. Dash, for this opportunity and for the kind introduction. I hope I only live up to his expectation, because I am really feeling intimidated after such a fascinating illustrated lecture by Dr. Bhupati Chakraborty. maybe I'll be taking you to the domain of little dry mathematics. But I'll request the students to keep their calculator maybe available on their cell phone or whatever, maybe a piece of paper ready with them so that you can actively interact with me while listening to my lecture. Coming to ISCS is indeed nostalgic, and I must compliment Dr. Bhupati Chakraborty for taking me to a further nostalgia of 1968, the most fascinating Olympics. He told already that it was held at more than 4,000 meter altitude, and it gave birth to so many records. The first time the 10-second barrier was broken in 100 meters by Jim Hines in 1968 Olympics. Likewise, the 20-second barrier in 200 meters Olympics by Tommy Smith, again in 1968 Olympics. The 44-second barrier in 400 meters by Lee Evans, again in 1968 Olympics. And a new record, I don't exactly remember the timing, by Kipchukino in 1500 meters run. So that was a fascinating Olympics, and thanks to Dr. Chakraborty for taking me to that journey also. As was suggested to me, the topic mathematics, the queen and servant of science, and normally I have been teaching physics, and I found that the students at times are very much anxious to what they call the derivations. They want to rote learn the derivation, and they feel very happy, they feel quite relieved when they are through with a particular derivation. So this particular attitude is looking upon mathematics as a servant. You must look upon it as the queen. And this was a book by by Eric Temple Bell, who was a fascinating science writer and a science fiction writer. And mainly, he took us through a journey through the works of geometry by Euclid, and then by Riemann, and finally to the theory of relativity by Einstein. Now, coming to the level, and particularly the target group which I am addressing, well, I'll try to bring it to the popular level, and I'd like to look upon mathematics more as the fun part of it. But before that, I'll just ask you to visualize certain things. I've purposely not prepared PowerPoints corresponding to that how mathematics as a queen exercises her command. I'll take a very, very simple example. Say, the use of dimensional analysis. You know the very simple fact that quantities having different dimensions can be multiplied, can be divided. Mass into velocity is momentum, mass divided by volume is density, but you cannot ever add mass with velocity. You cannot ever add mass with volume. If you want to add two quantities, or if you want to subtract quantities, they should always be unidimensional. They should always be unidimensional. In fact, I remember one student, while working with Maxwellian distribution, he wrote the expression a to the power of minus bu square in the examination hall, and he was unable to recollect what is the value of b. It is m by 2 kt or 2 kt by m. So then I went up to him. Well, I didn't punish him, but I told him that since you are in dilemma between m by 2 kt and 2 kt by m, just apply the dimensional method. M u square is energy, and kt is also energy, Boltzmann's constant times time. And so energy by energy is dimensionless, and anything appearing in the power of E has essentially got to be dimensionless. 1 plus x square by factorial 2 plus x cubed by factorial 3. So if that x is a quantity which has some dimension, a havoc gets created, isn't it? So this is something which I would like to impress upon you as regards the two very fascinating fundamental constants which acted as sort of iconoclasts during the last century, particularly 1900 to 1930, related to quantum mechanics and relativity. The constant related to quantum mechanics is very small, that is Planck's constant of the order of 10 to the power of minus 34 June 2nd, and the constant related to relativity is the velocity of light, which is a very big constant. And I am recollecting the Bohr's theory. Most of the students would be knowing, particularly the dispute with the Rutherford model. This does not require an elaboration, but Bohr's I beg your pardon, Bohr removed that dispute by standardizing the orbits. And he said that the electrons are rotating in stationary orbits, and in order to standardize the orbit, he could have taken several parameters, velocity, linear momentum, so on and so forth. But he had chosen angular momentum, isn't it? He had chosen angular momentum. Because one of the concerns of Niels Bohr was that he had to select a conserved quantity. And so the quantities at his disposal was energy and angular momentum. You would be knowing that in the case of a central orbit, angular momentum is conserved. And while writing that result, he had to depend on h, the Planck's constant. Now, have you ever wondered, just work out the dimension of angular momentum, moment of linear momentum, r into mv. R is length, m, L to the power of -1, so that becomes m L squared to the power of -1. And what about Planck's constant? It is energy into time. Energy is m L squared to the power of -2 into time, again m L squared to the power of -1. So don't you think that it's a gift of the nature that angular momentum and Planck's constant have the same dimension? Otherwise, however great physicist Niels Bohr would have been, he would not have been able to write that equation mvr is equal to nh by 2 pi. N and 2 pi are dimensionless. mvr is equal to nh by 2 pi. So see how the Queen exercises her command. After the theory of relativity, when the space-time interval had to be written, any space interval with 3 coordinates was quite simple. I'm telling about the square of the space interval that comes to x squared plus y squared plus z squared. But when time, about which the chairman is very much concerned now, is the 4th dimension. Now how to bring in at the same footing with length? Now while writing space-time interval, you cannot write x squared plus y squared plus z squared plus or minus whatever t squared. As I said, that you cannot add and subtract quantities which have different dimensions. So in order to make it unidimensional, you have to bring in a velocity. Forget about velocity of what, but you have to bring in a velocity to make it unidimensional. You have to multiply t with c. And we keep telling space with time. How far is Garihar Junction from here? Now half an hour if I walk, 10 minutes if I take a bus, and so on and so forth. So we are mentioning distance by time, keeping in mind some velocity. But when that velocity has to be the fundamental translational factor between space and time, it should be a standard velocity which has to be independent of the notion of the space of the observer and the source. And such a velocity, according to the special theory of relativity, is the velocity of light. Simultaneity is relative, time interval is relative, length is relative, but velocity of light is absolute. And so the space-time interval will, I'm not going to elaborate that, x squared plus y squared plus z squared minus c squared t squared. We had to bring in a velocity, if not for anything else, for the concern of unidimensionality. Again, the Queen exercising her command. You will be reading about laws of reflection. I can give umpteen number of examples. Laws of reflection, laws of refraction. And once you go to the genesis, well, we would always like to finish a particular activity in the shortest possible time. Again, a concern with the chairperson. That we are concerned about the time. You want to reach from here to some place, you would like to go in the shortest possible time. The same is followed by light. Once it goes from a point A to B, be it through the phenomena of reflection, be it through the phenomena of refraction, it has to choose a path for which the time is least. In fact, in ultimate analysis, we say the principle of least action. I am not going into that particular depth. For you should understand that the time required should be least. And once you make a calculation using simple differential calculus, the principle of maxima and minima, you arrive at the laws of reflection and the law of refraction. So the Queen exercises her command. And as Professor Dash was saying, that many of you may dread mathematics, and so I'll try to bring about the fun aspect to understand how it serves. And following him, in fact, he had suggested me to tell something about Srinivas Ramanujan and his association with his mentor, Hardy. As you know, Hardy was not only his mentor from the mathematics point of view, again from the health point of view. When in UK, most of the time Ramanujan used to be ill, and Hardy would come to him every day, but most of the time when he was at the hospital, and would scold him that you have not taken medicine, you have not taken food properly, and so on and so forth. Now, on that particular day, most of you would be aware of this particular story, that Ramanujan was quite cheerful, but again Hardy came and sat silently beside his bed. And then Ramanujan asked, what happened? Every day you come and scold me, but today I am cheerful. Why are you looking so morose? So he said that, well, while coming I took a cab and I found the number of the cab very boring. It's a bad omen. O-M-E-N, omen. Then Ramanujan asked, what's that number? And back came the reply that it is 1729. Now Ramanujan said that you are calling it to be a boring number. There cannot be a more exciting number than this. There are several numbers which can be expressed as sum of two cubes in two different ways. Sum of two cubes in two different ways, and 1729 happens to be the least among them. It is 1000 plus 729, 10 cube plus 9 cube. It is 1728 plus 1, that is 12 cube plus 1 cube. So least among the numbers which can be expressed as sum of two cubes in two different ways. And now this much is written in several books, several popular articles regarding Ramanujan, but you will be fascinated to know the number of interesting properties this number has. It is called the Harshad number. If you call in Hindi, jo harsh jagata hai, once it creates happiness. Now a Harshad number is one which is always